when we, historically talk about cancer treatment, our minds often jump straight to chemotherapy. And that word, it just carries this heavy baggage of extreme toxicity. For decades, the only way we knew how to fight cancer was with these blunt cytotoxic agents.
Right.
Drugs that just kill all cells that divide quickly, whether they're cancer or not.
That really is the baseline we have to acknowledge. Traditional chemotherapy, using drugs like antimetabolites or alkylating agents, it's really a numbers game. It's successful. I mean, it has cured cancers like acute lymphocytic leukemia in children and Hodgkin lymphoma.
Yeah.
But the collateral damage is just immense.
Because it's so indiscriminate.
Exactly. It just targets rapid proliferation. So it damages bone marrow, the gastrointestinal lining, hair follicles, everything.
And that extreme toxicity is precisely what we are moving away from. So today we are doing a deep dive into the revolutionary shift in oncology, the rise of targeted therapies. This isn't just a slight improvement. It's a fundamental change in philosophy.
Our mission here is to really understand this precision approach. Targeted therapies capitalize on molecular biology, and they move treatment away from that broad cellular lamage towards selectively affecting specific known molecular mechanisms.
The very things that are driving the cancer cell's growth.
The very things. So this area is, well, it's easily the most dynamic and rapidly expanding field in drug development right now.
So if we had to define the difference maker right up front, traditional chemo is cytotoxic and broad, often needs an IV drip.
Right.
Targeted therapy, on the other hand, is designed to inhibit a specific molecular target, an enzyme, a receptor, something like that.
And many of these new agents are conveniently oral, which is a huge plus for patients. And they aren't purely cytotoxic either. They're a mix of cytostatic agents, which stop growth, and then cytotoxic ones, which actually induce cell death.
Okay, so let's quickly set the stage using the old framework, just so we can really appreciate the new one. Traditional chemo agents were categorized based on when they attacked the cell cycle.
Right. We had our cell cycle specific, or CCS, drugs. They acted only when the cell was actively preparing to divide, so during the S, G2, or M phases.
And then the other kind.
Then you had the cell cycle nonspecific, or CCNS, drugs. They could kill cells even when they were resting in G0, though they were still generally more effective against the cycling cells.
So that system meant we were always operating with this massive safety margin issue. We were targeting the symptom of cancer, that rapid division, not the root cause of the disease.
Exactly. The real revolution, as you said, it bypasses that messy, broad DNA interference. We are now targeting the unique molecular scaffolding the cancer actually uses to survive.
So we're stepping away from just damaging DNA.
Completely. We're moving to interfering with specific protein-to-protein communication, which often begins with things like hormones or growth factors.
Which is a perfect segue. One of the earliest examples of this kind of precision targeting involves hormonal agents, right? Used mostly for hormone receptor-positive cancers, like a huge percentage of breast cancers.
Right, because these cancers are just fundamentally dependent on hormones for their growth.
But you starve them.
You starve them. This strategy is fascinating because it doesn't try to kill the cell directly, it tries to cut off its fuel. And the first major class here is the selective estrogen receptor modulators, or SERMs. The classic example is tamoxifen.
Tamoxifen is such a clever drug because it's almost duplicitous. How does it manage to slow the cancer cell's growth?
Well, tamoxifen is chemically diverse, but it can bind directly to the estrogen receptor, the ER, inside the cell.
Okay.
And when it binds, it competitively blocks estrogen from getting in and activating that receptor. By taking estrogen's place, it just drastically reduces the transcription of estrogen-regulated genes.
The genes essential for cell growth.
The very ones. So this results in a block early in the cell cycle, the G1 phase, which makes it primarily cytostatic in the breast.
So that's the selective part, the antagonist activity in the breast tissue. But this drug is, well, it's famous, maybe infamous, for its dual nature. It acts like estrogen in other parts of the body.
That dual function is so crucial for clinicians and patients to understand. While it's blocking growth signals in the breast, it acts as an agonist. It mimics estrogen's effects in tissues like the endometrium.
Okay, so we've solved one problem blocking breast cancer growth, but we've just introduced another potential systemic risk.
Right.
What are the clinical consequences of that agonism?
The primary risk, and it's a big one from that agonistic activity, is an increased risk of endometrial hyperplasia and uterine malignancies.
Wow.
It is a serious enough complication that it carries a black box warning. And on top of that, tamoxifen also carries a black box warning for increased thromboembolic effects. So, an elevated risk of DVT, pulmonary embolism, and stroke.
It's a powerful drug, but that selectivity is definitely imperfect.
It is. It requires very careful patient selection and monitoring.
That complexity really shows how early targeted therapy operated. Now, if tamoxifen tries to block the receptor, the other major class of endocrine therapy, the aromatase inhibitors or AIs, they just try to eliminate the fuel supply altogether.
Precisely. AIs, like anastrozole and letrozole, they work by inhibiting the aromatase enzyme.
Okay, and what does that enzyme do?
This enzyme is responsible for the peripheral conversion of androgens, things like androstenedione, into estrogen, specifically estrogen in your non-ovarian tissues.
Ah,
So by inhibiting aromatase, we achieve selective estrogen deprivation.
that sounds like a much more definitive strategy than just blocking the receptor. Are there different kinds of AIs?
Yes, we typically differentiate between type 2, which are non-steroidal competitive antagonists like anastrozole, and then type 1, which are steroidal irreversible inactivators like exemestane.
But they both do the same thing functionally.
They both achieve the same goal of stopping estrogen production, yes.
And strategically, when do clinicians use AIs?
They're particularly effective in advanced breast cancer. And critically, because they block that peripheral conversion, they're only indicated in postmenopausal women who rely on those peripheral sources of estrogen.
And the trade-off?
The main trade-off is directly linked to the deprivation itself. Significantly lower circulating estrogen can lead to decreased bone mineral density and a much higher risk of fracture.
Okay, so hormonal therapies were the early wave, focusing on those intracellular receptors. But the next massive leap came when we learned how to target signaling pathways on the cell surface. The tyrosine kinase inhibitors, or TKIs, this is where we really get into true molecular personalization.
Oh, absolutely. If endocrine therapy was blocking a door, TKI therapy is like turning off the master control switch. And the discovery and development of imatinib, which is known commercially as Gleevec, is probably the single greatest story defining the era of targeted therapy.
And that story starts with a very specific genetic abnormality, the Philadelphia chromosome. So tell us why this fusion protein was such a perfect target.
It was just a perfect storm of vulnerability. The Philadelphia chromosome is a translocation that creates the BCR-ABL fusion protein.
Okay.
And this protein is a constitutively active tyrosine kinase.
So what does that mean in simple terms?
If you think of a kinase as an enzyme that acts as a signaling switch, telling the cell to grow and divide, this BCR-ABL protein is a switch that is perpetually stuck in the on position.
It's like a car with the accelerator pedal just jammed to the floor.
That's a wonderful analogy. It is constantly driving proliferation, which is the absolute hallmark of chronic myelogenous leukemia, or CML.
So imatinib comes along. What does it do to that stuck pedal?
Imatinib is a small molecule that competitively binds to the kinase site on that BCR-ABL protein. It gets there first, it binds tightly, and it prevents the activation process. It just stops the downstream signaling cascades cold.
So it jams the signal.
It jams the signal and forces the cancerous cell to stop dividing and enter apoptosis. And this turns CML from what was often a rapid death sentence into a chronic, manageable condition, almost overnight.
That magnitude of clinical shift is why this is such a powerful story. But even these precision weapons have trade-offs. What are the typical toxicities for imatinib and its successors, like dasatinib?
The side effects are systemic, but they're generally much more manageable than traditional chemo. You see things like diarrhea, muscle pain, myalgia fluid retention, edema, and a risk of congestive heart failure.
And I imagine resistance is an issue.
Oh, yes. Newer generation TKIs like dasatinib and nilotinib had to be developed because inevitably cancer cells develop resistance, often through mutation of the very BCR-ABL gene that imatinib targets.
Now, TKIs aren't just used for single oncogenes. They're also deployed to shut down broader processes necessary for tumor survival, specifically angiogenesis.
Right, the formation of new blood vessels.
And this is where the anti-VEGF TKIs come in.
Tumors need a blood supply to grow beyond a microscopic size. And VEGF, vascular endothelial growth factor, that's the signal that tells the body to build new vessels to feed the tumor.
So drugs like sunitinib and sorafenib.
They inhibit multiple receptor tyrosine kinases, including those associated with the VEGF receptor family, and they effectively starve the tumor.
And we see a very distinct side effect profile emerge when you start inhibiting vessel formation across the body, don't we?
We do. Since you're interfering with a crucial system governing vessel health, you see vascular issues,
Yeah.
high blood pressure hypertension, an increased risk of arterial thrombotic events, bleeding complications, and sometimes even gastrointestinal perforation.
It's the predictable systemic consequence of messing with a fundamental system.
Exactly.
So, if TKIs are dealing with signaling and angiogenesis, we also need to address the central command for cellular growth and metabolism, the mTOR pathway.
The mammalian target of rapamycin, or mTOR, is a master regulator. It integrates all these signals related to nutrient availability, energy, growth factors, and it uses them to regulate cell division and protein synthesis.
So inhibitors like everolimus and temsirolimus.
They just block mTOR activity, and that results in the tumor cells hitting the brakes. Specifically, you get a G1 growth arrest.
We often see these used in advanced renal cell carcinoma, but their mechanism, it affects more than just the tumor cells, right?
Yeah.
Especially when it comes to the immune system.
That's a critical point. mTOR is vital in so many cells, so inhibiting it causes profound myelosuppression, especially thrombocytopenia. And because it modulates immune response, it leads to an increased susceptibility to infection.
So that's why they carry that black box warning.
It is. Due to the immune suppression and the potential for secondary cancers like lymphoma, these drugs carry a black box warning for the risk of developing secondary malignancies.
That brings us to what feels like the most modern, almost philosophical approach to cancer targeting. Drugs that don't just stop growth, but actually weaponize a cancer cell's own defects. I'm talking about PRP inhibitors.
And the concept of synthetic lethality, this is truly elegant science.
It really is.
So PRP stands for poly ADP ribose polymerase. The PRIP enzymes are essential for fixing everyday DNA single-strand breaks. They're like the quick fix crew.
Okay, so what happens if we use a PRP inhibitor, something like olaparib, on a normal healthy cell?
A normal healthy cell has two main ways to repair DNA damage. PRP is the secondary quick path, but the major robust repair system relies on proteins like BRCA1 and BRCA2.
Okay.
So if you inhibit PRP in a healthy cell, the cell just says, okay, and relies on its excellent BRCA machinery. No big deal.
But the whole strategy is to deploy these against tumors that are already BRCA deficient. They've already broken their main DNA repair path.
Exactly. This creates what we call synthetic lethality. The BRCA deficient cancer cell already lacks its major repair mechanism. Then you come in with the PRP inhibitor and you disable the cell's minor quick fix repair mechanism too.
So it has no backup.
No backup at all. The cell just accumulates catastrophic DNA damage because it has no way to repair itself, and it dies. It's a targeted kill achieved by exploiting a pre-existing flaw.
It's precision. It specifically targets the cells that have that BRCA vulnerability, which is why it's so effective in tumors like advanced ovarian cancer or certain breast cancers with the mutation.
And the toxicity profile reflects this DNA disruption. While it's usually manageable, these agents do carry a risk of developing serious secondary hematologic cancers down the line, specifically myelodysplastic syndrome, or MDS, or even acute myeloid leukemia, AML.
But the benefit of turning an aggressive cancer into a manageable disease often outweighs that low long-term risk.
For a significant amount of time, yes.
So we've seen this incredible journey today, from general cytotoxic agents that killed everything that was dividing to this molecular scalpel. We saw tamoxifen blocking estrogen transcription, imatinib jamming a constitutively active fusion protein.
And PRP inhibitors exploiting those BRCA deficiencies to induce synthetic lethality. The focus has shifted entirely from broad cell destruction to disrupting specific biological pathways.
The quality of life improvements have been huge.
They have. However, as advanced as these drugs are, we always run into oncology's biggest hurdle, drug resistance.
Right. Cancer cells are just masterful at adapting. What are the common escape routes, especially from these highly specific therapies?
Well, resistance mechanisms can be annoyingly simple or incredibly complex. On the simple side, you have general resistance, the increased expression of the P-glycoprotein transporter.
What's that?
It's a cell surface pump. Think of it as a universal security guard that just actively spits out many different classes of anti-cancer drugs, regardless of what their target is.
Wow.
We call this multi-drug resistance, or MDR.
So we create this incredibly precise key for the lock, and the cell just builds a high-powered pump to eject the key as soon as it gets inside.
Precisely. And then you have the more specific resistant, like the mutation of the BCR-ABL gene that makes imatinib unable to bind effectively. It's an evolutionary arms race played out at the molecular level.
Which leaves us with a compelling final thought for you, the learner. If cancer cells are already experts at developing these broad resistance mechanisms like the P-glycoprotein pump, does the sheer precision of these targeted therapies, hitting just 1 or 2 points, actually force the cancer cells to evolve new, highly specific resistance mutations even faster? Or, conversely, does the modular nature of targeted therapy allow oncologists to simply deploy smarter, multi-layered combination therapies, like stacking TKIs with PRP inhibitors, to effectively stay 1 or 2 molecular steps ahead of the cancer's evolution? Think about how these resistance mechanisms dictate the speed and shape of the next generation of combination treatment strategies.